before we start, I just wanted you to give a round of applause to Saeed, who's been organizing all this. And it's a stellar turnout today. We are expecting to see nearly 50 people. It's a huge improvement on last year's event. I think Saeed has done an amazing job to attract such a wonderful audience as you all are. So, in the run-up to the festive season, this is a very special time when the three founding fathers, if you like, of Thalesians, the three originals, and I'm not being modest because I'm including myself there as well, are all here in London to gather and listen to a very interesting talk and share a meal. And I think it's a great opportunity. I'm really excited about it. Matthew is our speaker today. I'm not going to read the title of his talk, which is very, very complicated. Complicated for me. I'll just say literally a couple of words about Matthew, unless you have met Matthew. Matthew is now based in the States, and he runs our US operation. So, as befits a Thalesian, he has a stellar academic record as well as a stellar industry record. In addition to being managing director and head of Americas at Thalesians, he is an assistant professor of finance in the Stuart Business School at the Illinois Institute of Technology. His research focuses on the application of advanced computational techniques to financial modeling and data analysis, especially where high performance and scalability are critical for practical application. This will be of particular interest to the high performance computing community among you. Matthew's research is currently funded by Intel Corporation. He has contributed to the R-Package repository and published around 20 peer-reviewed technical articles. He has taught financial econometrics, derivatives, machine learning. I believe you will be talking about machine learning in this talk, another big topic for Thalesians. And he has taught financial econometrics, derivatives, machine learning, and text mining at the University of San Francisco and held visiting appointments at Stanford and UC Davis. Prior to joining academia, he has held industry appointments as a quant at banks such as Lehman Brothers, the Bank for International Settlements, and Barclays Capital. He chairs the workshop on computational finance at the annual supercomputing conference and serves on the program committee of HPC and on the editorial board of the Journal of Financial Innovation. And today, it's a great pleasure to welcome Matthew. Please join me.
Well, thanks very much, and I'll try to project my voice so that you can hear me in the back. I know there's a little bit of background music, not sure. But if you can't hear me, just sort of signal that I'm a little bit mute. Okay, wave your hand or something, and I'll try and remember to increase my tempo and my volume. And so, what I'm going to be talking about today is research in progress. I have to confess, I'm not a trader. I've not traded with this. My intention is to do so, but as of now, I have not traded with it. So if you're looking for hedge fund performance figures, Sharpe ratios, maximum drawdown, you're not going to see that in today's talk. What I'm going to talk about more is the ideas around how to take data, in particular intraday data, and turn that into useful features for machine learning. And I'm going to be talking about some advancements in hardware which facilitate more extensive, more compute-intensive machine learning that probably wasn't possible 10 years ago. So this is in collaboration with the Northwestern University Financial Engineering, Industrial Engineering Group. The work is funded by the Intel Corporation, who have a vested interest in selling their Intel Xeon 5 to various hedge funds and banks. And I mainly specialize in the area of programming sort of compute-intensive problems and trying to get optimal performance out of fairly complicated algorithms which usually require understanding the math. So I'm going to give some math today. Usually I don't give this talk to mathematicians. I usually give it to finance and sort of traders because they don't give a damn about the math. But out of sort of service to some of you here, I know you have a math background, I wanted to show a little bit of the math. But if I'm getting too bogged down in the math, please raise your hand or throw something at me, because I tend to get bogged down in the math. So let me stand back for a moment, and I should say, you know, this talk should take about 40 minutes, and I know that we're all sort of eager to get started eating, so I'm going to try and get this in 40 minutes. But really what we're trying to do here is engineer automated trading decisions. And how we do that is essentially somewhat of a gray area. It's a research area that's been obviously visited and put into practice over and over again. And I would say generally, having spoken to many traders in Chicago and New York, there is a great deal of skepticism about what the value out of machine learning can be. And so I'm going to try and talk a little bit about that, not as someone who's, you know, hell-bent on making machine learning work, but more on what areas are the weak points and where, or how can you improve it, and what do you have to do to the data in order to be able to sort of improve the performance. But I'm not going to sort of say that deep learning or machine learning is a magic bullet. So that's the first caveat. And I'm going to also talk about the importance of using machine learning with advanced architectures. So again, you know, very simplistically, we're taking market data, whatever that is, at high frequency. That can be many things. We could be looking at MDP3 formats for binary encoded feeds from CME exchanges, and then looking at, you know, the delay from the exchange to the when it's received. It could be looking at various different signals. I'm not going to be looking at the high frequency data set here at level 2 order book data. I'm going to be looking at 5-minute snapshots, and so the microstructure is less of a concern here. And that's partly because that's the data I got access to. I've now got access to some high frequency data, and I'm looking at what kind of features could be useful for predicting various arbitrage opportunities, either deeper in the order book or across different asset classes in the inside market. Essentially, we have a bunch of rules, and we have a set of configurations, and then we try to make a trading decision. Now we know from our great friend and hero of today, DePrado, that the more configurations we have, the more backtesting period we need. He recently published a number of papers or sort of bullet points stating the problems of machine learning when you go to backtest. There is a tendency to, because we can just increase the number of configurations, we can overlook the fact that we can massively overfit because we're not using more backtesting data. That's a sort of a side note, something I'm not going to talk about today, but I find the whole area of backtesting with machine learning a very interesting topic, and it's by no means it's a very nuanced area. So if that's the sort of the picture, then what kind of markets have I been looking at, or what in particular what markets are interesting to look at? And I've been looking mainly at CME futures contracts and less at equities, primarily, and also FX. So, and I've been looking at these at sort of intraday level, and obviously there's scope for looking at interest rate markets, treasuries in particular, and option markets. But I've seen, at least in Chicago, there's been more interest in using machine learning methods as being within FX and commodity futures. Probably not surprisingly, it's where the CME is located. So what we have to do, of course, at a very simplistic level, is we have to choose a strategy. We have to pick a certain set of configurations. It could be what the slow-moving average is and what the fast-moving average is. And then we have to determine what is a buy and a sell signal. And it could be crossing over within some tolerance, and we can obviously measure this historically to see what kind of Sharpe ratios we get. And this would be a very simple sort of example of a strategy, but there's no machine learning at this point involved in coming up with a strategy like this. So what we want to do essentially is go a little bit further and say, well, how can we engineer a strategy producing buy and sell decision? rather than sort of taking what sort of heuristically or ad hoc or sort of by gossip or word of mouth seems to have worked well. You should pick a long moving average of 200 days and a short moving average of 50 days. It seems somehow plucked out of thin air. Maybe there's a possibility here of using machine learning to explore different strategies and different configurations, with the caveat that we need to be very careful when we're looking at backtesting of data. So again, I'm building up all of this before I start talking about deep neural networks, because essentially the essence of the idea is that we have a configuration, or rather we have a set of configurations. For example, within the mean reversing strategy, the moving average crossover strategy rather, that would be, say, the long window, the short window, maybe some tolerance between those two averages crossing. And then we make a trading decision, either to buy, to hold, or sell. And again, we may have some tolerance within this hold period. We might be looking for, say, a one standard deviation signal or something. It may not be obvious what the threshold is between the zero and the buy and the sell. And I'm going to be talking a little bit about that because that turns out to be quite an interesting area for machine learning. And then we go ahead and we use our favorite utility function, whether it's a combination of P&L, a cumulative P&L, maximum drawdown, Sharpe ratio, relative to a benchmark. If it's intraday, probably not so much. But if it's end of day, we may be measuring against some kind of benchmark. So the idea is then we have our strategy configuration. We collect a set of data or features, and then we pass that to not a regression model, but a classifier. We want to directly predict whether to buy, hold, or sell. And then we're going to measure that out of sample and see how well our classifier performs. So this is already a big departure from the literature, which tries to actually predict or forecast the value of the stock or the underlying itself. What we're trying to do here is say, well, that data is too noisy. Let's move away from trying to predict the actual price, and let's just come up with an automated way of making a decision. That's the classifier. So, neural networks got a really bad rap, probably in the mid to late 90s. There were a lot of people who got very excited about neural networks, and they claimed all sorts of sort of performance results, and very few people seem to be talking about them today. So my impression is that they certainly didn't sort of, for some reason or other, they didn't hold up. And reasons are, for a number of reasons, it's overfitting to the data. It's just that the data is just too noisy, and somehow, they were using the wrong performance metrics. Performance metrics don't matter to traders. They matter to computer scientists, but not to traders. And so there are a number of sort of disconnections or sort of lack of rigor in application. And since then, of course, we've seen movement towards higher frequency data, and we've seen a wider number of instruments being available over listed exchanges, and so it's kind of interesting to revisit the problem, particularly when we've got another story in the picture, in that computer hardware has fundamentally changed. And this means that, with every sort of major shift in hardware innovation, there's an opportunity to do something different with methodology. And in some sense, that's what happened with neural networks. Parallel computing became sort of possible in the 1950s, and neural networks became very popular as a result of that. And we've seen this sort of saturation here, where there's unsustainable heat dissipation on a processor, and now we've of course moved away to the era now where we've got teraflops of computing power that we just slot into our servers. And by the way, I should say that the next generation of the Intel Xeon 5 coprocessor is about the size, about 1 inch by 1 inch. It's going to be a die on the motherboard. It's not going to be through a coprocessor anymore, and it's going to have something like 70 cores. It's going to have something like 2 teraflops in double precision. That's around 250 40 degrees of parallelism, and we're really dealing with enormous amounts of compute power here. The question is, why do we care? As traders, as quants, why should we care about having more advanced computer architecture? Which now we can just program in C++, we don't need to write CUDA or any of this other stuff that created a huge amount of headache. Well, I personally think it's very exciting because it enables us to use machine intelligence to explore the configuration space of strategies and parameterizations and try to find what are the best types or develop meta models or combinations of machine learning methods which hold up under different market conditions. So in some sense, we're really dealing here with an intersection, especially at high frequency, between having to process very large amounts of data, possibly tick-by-tick level data, and on the other hand, we're dealing with enormous amounts of computation which are required to train the models and then test them. And we're also seeing at the same time that deep learning is sort of appearing as a prominent new machine learning technique. It won the famous sort of cats and dogs competition that Kaggle put together, and it's being used by Siri, and it's being used and recently run the large-scale visual image recognition competition as the best method for detecting visual faces, patterns. The intuition is that deep learning allows you to explore more complex nonlinear relationships than you could with, say, a single layer neural network or even a support vector machine or any of the other methods. So DeepMind is, of course, hard at work making sure that Mario Brothers can be played sort of automatically and doing other things like automatically flying drones. Very interesting work. But like anything, is it really useful for finance? And this is the question which I've been battling with. I've tried to remain as agnostic as possible and not be sort of sold into the, there's an enormous amount of, coming from Silicon Valley, there's an enormous amount of drinking the Kool-Aid, use deep learning, series, it's being used for Siri, it's being used for all these applications. But if you think about it, DeepMind isn't looking at finance. And I've spoken to a couple of guys at Google DeepMind, and the finance is way too difficult. You stay away from that one. And so the interesting thing is, okay, so we've got all these interesting machine learning methods, but somehow we're not really seeing them sort of reaching their true colors within the finance domain. Now, why is that? And I think part of the reason is because we just don't have the amount of resources of academic researchers looking into this kind of thing. There's no money on the table for it. There's funding for defense research, there's funding for all sorts of other applications, whether it's visual recognition. I can go and apply for $1 million grant right now to study computational biology or look at the astrophysics, but I don't because I'm interested in finance. So there's a lot of money on the table if you're interested in applying deep neural networks to scientific applications. There's nothing if you want to apply it to finance. So that's one of the problems. So let me sort of gently walk into what deep neural networks are. And I'm going to start very conceptually and then get more into the details of the mathematics. And then I'm going to show you why it's actually very difficult to train deep neural networks without some kind of advanced computer architecture. And again, this is the kind of technology which Google is running, but they're using GPU farms, they're using tools like Xeon, using obviously TensorFlow, and Caffe, another example of a C++ language which implements deep neural networks. But this is a very computationally intensive process, starting with the building blocks being the perceptron level. And probably everyone here knows what a perceptron is. It's essentially providing a set of weighted inputs. These can be considered features, whether they're some kind of price or returns at a daily increment, or it can be snapshots of best bid offer prices. These could be some other features which we engineer, which I'm going to talk a lot more about, because that turns out to be very important for the success of the method. And then we feed it in, we compute the weighted sum. We actually add a bias term here, which I haven't added on the diagram. And then we usually apply some activation function to sort of smooth out the result. And this can be usually a sinusoidal or a hyperbolic function. It can also be what's called a softmax function. And then we get some output. And we measure that output against the observed output. We see how well the model does using various different metrics, which I'm going to talk about. And then we retrain or we relearn the weights. So in a simplest possible model, where we have just one perceptron layer and one hidden layer there is, this is what's called a feed-forward, fully connected neural network, where every single neuron or perceptron, I'm going to use neuron and perceptron interchangeably, connects to the neuron in the next layer. It doesn't have to, and there's a lot of science, or not sure if I would call it science, but there's certainly an art in selecting whether or not to connect one node from previous layer or perceptron to the next one. But in the simplest possible case, we have a fully connected feed-forward network. The inputs come in here from the left. I know it's a little bit difficult to see the beamer here, sorry about that. And we then propagate by taking the weighted sums, applying this activation function inside this little red blob here, and then advancing that to the next layer, and so on. And so the next level of complexity, of course, is to just add more layers. So within, again, I'm not sure how well you can see this at the back, but within every single sort of little blob here, we have this perceptron. Inputs are going in, they're being weighted, and we are then summing them, applying this activation function, and then propagating that to the next one, and so on and so forth. And we've already got a number of problems to deal with. Like, how many perceptrons should I have in this layer? How many layers should I have? Should I be tapering inwards? What type of function here should I be applying to regularize the gradients that you can get from inside here? What type of algorithm am I going to use to back propagate the information and retrain the weights? So, and how am I going to train this? And so I can tell you now that when you start to think about this, you're suddenly overwhelmed with a number of parameters that have to be thought about. And the story gets even more complex. Not to get too discouraging, but there is, I'm not trying to say that deep neural network is easy. The converse, I'm trying to say it's actually quite difficult. But I'm going to try and convince you through preliminary sort of research that there may be some merit in this approach. So in a deep neural network, and what we do is increase the number of layers so that it's considered sufficiently deep. What constitutes deep is somewhat subjective, but typically at least 4 or 5 layers is what's normal. How many layers you need, again, is somewhat of an art. There is no theory to say how many layers you need. And there's absolutely no reason why there should be the same number of perceptrons in each layer. Typically, what I've seen is you start with a very large number of inputs, and you tend to funnel inwards and have a very small number of outputs. So with this sort of conceptually in place, at least the idea in concept, let's start by now sort of firming up the sort of what we're actually doing at a mathematical level. And again, this is fairly light. It's sort of at the an engineering mathematics level, not at a sort of a pure applied math level. But what we're going to do is essentially specify this problem more rigorously by saying that in each layer, that's the supremum of this bracketed element, it doesn't look like a power sign, we have a set of weights, or a vector of weights applied to each of the perceptrons in the nodes. And then we have big L number of layers. And so what we're trying to do here is we're trying to find the optimal weightings in order to minimize this cross-entropy function. And what I've done here is N denotes the observation in the data. So we may have a row of features, and what we're doing is we're computing this sort of element-wise or row-wise entropy term for each observation in the data. So we may have, say, 5 million observations, and then we may say hold out 100,000 for testing, just to evaluate the performance on the holdout.